Now it's time to start. Good morning to everybody. Good morning to respected dignitaries and all participants. Today we are going to have a webinar on a very interesting subject, LVDC, low voltage direct current, the future of electricity usage. This webinar is organized by BIS and LARC, Lightning Awareness and Research Center of CISA. CISA is an NGO operating on various science subjects. We are making a campaign called Vidyut Surakshit Bharat Abhiyan. It's an year-long campaign for the purpose of increasing the electrical safety situation in India. All of you are aware that the electrical accidents and the the fire due to short circuit happening in our country. Mostly the fires are related, or people say it's related to the electrical reason. So our Vidyut Surakshit Bharat Abhiyan is a year-long campaign to train electrical engineers about modern electrical safety measures in homes and workplace, and to popularize the Indian standards on electrical safety. Most of the time, you are aware that the safety standards are misinterpreted in a large way. So the campaign have different classes on different subjects, and we educate how to read and understand a standard and how to apply it when you design or erect or test an electrical installation in order to reduce the accidents. The campaign started on 2nd July 2021, 2 months back, during the last day of Electrical Safety Awareness Week by Central Electricity Authority. The campaign is supported by BIS and participated by CEA, Indian Railways, ISRO, electrical inspectorates of some of the state governments, associations such as FOCUS, FSAI, Fire and Security Association of India, International Copper Alliance, South Asian Lightning Network, Spark Group, and a few more. A lot of training programs are being organized. There are training programs exclusively for the participating organizations such as ISRO, for example. Last week we had a program for 4 days on 8 different subjects, and it was actually that went very well. Similarly, 4 programs for Indian Railways are over, and this week, Friday and Saturday, we are going to have 2 more programs. Basically, the concentration is on the IS 732 and the upcoming National Electrical Code and all the IS standards in relation to that. Exclusive subjects such as solar PV, safety of solar PV, and safety in hospitals are also explained with. So our today's webinar, LVDC, the future of electricity usage, is about a new, interesting, and upcoming technology in electrical usage, which is going to be very important for our nation in future. The reason modern electrical and most of the electrical and electronic equipment operate on DC, all of you know very well. Internally, they operate on DC, and we are already in a LVDC world, but we don't realize it. And our renewable energy sources such as solar PV are producing power in DC. So the question is whether we can use the same DC for operating our electronic appliances, so that the in-between equipment can be eliminated and the energy efficiency can be increased. So we start this program with a small inaugural function, for which I would like to invite Srimati Preeti Bhatnagar, Head Electrotechnical Bureau of Indian Standards, for the welcome address. Srimati Preeti Bhatnagar is an electrical engineer by profession and has been working in BAS for more than 30 years. She has worked in different activities of BAS, in which like standard formulation, certification, and training. The major part of her tenure in BAS was dedicated to certification activity. So, welcome, Madam, and over to you, Madam.
Thank you, Gopalji. Jay Roy Choudhary, Deputy Director General Standardization. Shri N.S. Sodaji, Chairman, LVDC Distribution System Sectional Committee, ETD 50. Distinguished speakers, guests, ladies and gentlemen. A very good morning to all of you. It indeed gives me great pleasure to welcome you all on behalf of the Bureau of Indian Standards and Center for Innovation in Science and Social Action in this webinar for live interaction with stakeholders on the subject low voltage direct current, the future of electricity usage. Electricity is a key enabler of socio-economic development. UN's Sustainable Development Goal 7 attempts to ensure access to affordable, sustainable, reliable, and modern energy for all. And specifically, a time-bound target for delivery is stated through Target 7.1, which declares that by 2030, ensure universal access to affordable, reliable, and modern energy services. Now, low voltage electric current (LVDC) is seen increasingly as a green and efficient method of delivering energy, as well as a way of reaching the millions of people without any access to electricity who are located in very far off and remote areas. It's fully in line with the UN Sustainable Development Goal 7 of providing universal access to affordable, reliable, and modern energy services by 2030. Bureau of Indian Standards is driving the work relating to formulation of Indian standards on low voltage direct current power distribution systems and its promotion. Work related to formulation of Indian standards on LVDC power distribution systems comes under the purview of Sectional Committee ETD 15 under the Electrotechnical Department of the Bureau of Indian Standards. BIS has published the standard for guidelines for 48-volt extra low voltage DC distribution systems, that is IS 16711-2017. The standard covers the essential requirement for distribution of power from an extra low voltage 48-volt DC power source. These guidelines are the starting point for standardization of the enabling technology LVDC. It is anticipated that this will lead to rapid development of other relevant standards. This standard is expected to provide investment security to developing economies with generally secure international sovereign debt to finance electricity access projects. As a result, this establishes Indian standards firmly in the operational processes of the World Bank Group as well. I take this opportunity to thank you all for this overwhelming response and accepting our invitation to attend this webinar. Once again, I welcome you all to this webinar and hope the outcome will be very good. Thank you so much. Over to you, Deepaji.
Yes, thank you very much, madam. Now we have we welcome Shri Jay Roy Choudhary, DDG, Deputy Director General Standardization 1 of BIS, for his inaugural address. Shri Jay Roy Choudhary is a civil engineer by qualification and over 31 years of experience in BIS and over 35 years in overall experience. He has worked in different capacities in activities of standardization, international relations, products and system certification, and training in BIS. In his present role in DDG standardization, he leads the national standardization work in various technology areas and economic sectors. Over to you, sir.
Thank you, Mr. Gopakumar. Mr. N.S. Sodha, Chairman ETD 50, esteemed speakers of today's webinar, Mr. Mahindru, Mr. Rajesh Kunnat, Mr. Venkat Rajaraman, my colleague in BIS, Mr. Rajiv Sharma. It is indeed and other participants of today's webinar. A very good morning to you all, and it is indeed my pleasure and privilege to be amongst you all in this webinar on a very important subject of LVDC. And at the outset, I think I need to congratulate CISA for coming together with BIS in sort of having this program today. Since the advent of DC technology for distribution, which started in the early 20th century, things have changed a lot. By the 1920s, we all know that there were advances in AC technologies, which resulted in the development of large power plants, and then introduced the concept of central power stations. And with that, we came to distribution of ACs and electric power being largely provided through ACs. From a power, as far as India is concerned, from being a power surplus nation until the 70s, India moved to a phase of chronic shortage of electricity in the 90s, till we sort of recovered and emerged again as a power surplus country in terms of generation availability being always greater than the demand. The various power generation projects planned by the government, both at the center and in the states, combined with the application of new technologies to improve power and power efficiency, power energy efficiencies, like in the smart grid and smart energy context, indicate that we as a nation will be comfortable in the demand and supply equation at an aggregate level as forecast, I think, till 2050. The sources of power generation today are both conventional and non-conventional. India has an installed capacity, as we understand, of about 386 gigawatt, and electric energy consumption is about 1,300 gigawatt hours. So India already is the third largest producer of electricity in the world. So in this context, what we find today is that we are, from the consumption point, about 80% of the consumption is made through conventional sources, largely from thermal, oil and gas, besides hydro and nuclear sources. The rest is being made through the renewable sources like wind, solar, biomass and small hydropower plants. India is also in this scenario running the world's largest clean energy program to achieve 175 gigawatt of renewable energy, including 100 gigawatt of solar power. So this means that about 40% of the generation will be from non-conventional sources, as opposed to the current status of around 20%. So as you are aware that as a country, we face the challenge of ensuring universal access to electricity as one of the most important goals set for the energy sector by successive governments. I mean, it is true in India, it is true across the developing world also. And because we all understand the role that electricity plays in economic development, and it is an absolute necessity to provide access to electricity, not only from the economic considerations, but also to ensure that we are able to fulfill the various social objectives for inclusive development that we aspire for. In this context, I think low voltage direct current has the potential to explore and the use of DC for generation and distribution of electricity, with the possible usage of renewable energy sources amidst spreading global concerns like depleting fossil fuels, energy conservation, and more particularly of clean environment and the continuously growing demand for electric energy. Some of the other aspects of why we need to, I mean, the potential of LVDC and DC was highlighted by Mr. Gopakumar in his initial remarks. So the significance of DC and the role that LVDC can play, particularly in the developing world context, need not be highlighted any further. So it is felt that it would help feed the rural part of the nation, especially where electricity has not reached so far, by way of generation of DC power using solar and wind energy, and with the establishment of small microgrids or local microgrids, through which there would be distribution of DC supply directly to small houses, so that at least the basic requirements of household in terms of electricity through lighting, charging of mobile phones, or operating certain electrical gadgets, maybe a TV or refrigerator, all these can take place. So this all this will put rural Indian homes well connected to the outside world, and sort of foster the economic and or the socio-economic progress that we aspire for. To start with, I think DC supply is also being considered to be very useful for even cases like operating big data centers in urban areas where a lot of batteries are being used, and for their charging, the AC supply presently, which is being received from the utilities, is first converted to DC before it is further consumed. So there lies the potential of application of DCs in the urban context also. So given all this, I think LVDC has gained significant importance and the attention of the global community at large. It provides wider scope for generation and distribution of electricity with the possible extensive usage of renewable energy resources amidst the global concerns which I mentioned of energy conservation, of the environment, and so on and so forth. Incidentally, India has been leading this work as far as standardization is concerned, standardization of LVDC, and India is holding the chair of the Systems Committee in the IEC, International Electrotechnical Commission, and we have, of course, today amongst the speakers, Mr. Mahindru, who chairs this particular committee of LVDC in IEC. So I'm happy that this particular webinar on this very important subject would provide a platform where stakeholders and experts from across the country would have the opportunity to interact on the subject, to have a better understanding of the technical challenges that the subject may pose, and to get apprised of some of the developments and some of the intricacies associated with the subject that are being addressed through standards and other means. So I'm very confident that in course of today's deliberations, we would have a very good exchange of information and exchange of ideas and thoughts, which in the overall context, we all would stand to benefits, both from the stakeholders' point of view as well as from we as a standards body's point of view. So with these words, I welcome you all to this seminar and wish the deliberations all success. Thank you very much.
Thank you very much, sir. Now we welcome Sri N.S. Soda, former Executive Director of Power Grid Corporation of India Limited, for his keynote address. Sri Soda graduated in electrical engineering with honors from Malaviya Regional Engineering College, Jaipur in 1976. He also holds a postgraduate business management degree from AIMA. He was trained in the senior level management programs at ASCI Hyderabad, IIM Ahmedabad, IIM Calcutta, IIM Lucknow, and international management programs in UK and USA. So I would like to welcome Sri N.S. Soda for your keynote address. Over to you, sir.
Thank you very much, Mr. Gopakumar. Am I audible properly?
Yes, you are audible.
Thank you so much. And first of all, good morning to all the dignitaries and Mr. Roy Choudhary, Mr. Vimal Mahindru, Madam Preeti Bhatnagar, Mr. Rajiv Sharma, Ritvik Anand, and all my colleagues who are working in the LVDC group. It's really a pleasure to be speaking before an august audience. And I understand that hundreds of people are attending this seminar. It is, first of all, on behalf of Bureau of Indian Standards, I welcome you all in the Conference on Low Voltage Direct Current. Friends, I come from a EHV company called Power Grid, having spent most of my career with the Power Grid. So I'm conversant with the EHV AC, UHV AC, as well as HVDC. The Indian grid, which Mr. Roy Choudhary recently mentioned, handles about 200 gigawatts of power, as against the installed capacity of, say, 380 or 385 gigawatts. Certainly, we have a hybrid system, which is very unique in this world, where we have the EHV-AC, we have the UHV-AC, which goes up to 765 kV, ultra high voltage alternating current. And we have up to 800 kV plus minus HVDC, transporting 6,000 megawatts of power from, say, Champa to Kurukshetra, one link, and then another in the south. So HVDC plus EHV-AC and UHV-AC has made India a very unique electricity grid in the world. And certainly people look at us not only from the point of view of how this single nation, single frequency grid is being managed, 200 gigawatts, out of which the renewable component is hardly about 22% today, which is likely to be increased to almost 35 to 40% in the coming years by 2035, with the advent of 175 gigawatts of these renewable energy, about 100 gigawatts coming from the solar field. What I want to tell you is that the users in each home or each building or each office complex, most of the equipment that we are using, although they are connected to a 230 volt or 415 volt AC system, but many of them are virtually operating on DC, whether you call it LED lights, or you call it refrigerators or TVs or laptops or mobiles. Just for the sake of information, I think India has about 900 million, mobile users, about 90 crore, I should say. And you can imagine, even if 4 or 5 watts of electricity on DC is being consumed at the time of charging by these mobile phones, you can imagine the type of gigawatts that we are consuming. So virtually what is happening, that we are converting AC into DC at a lot of multiple points in our grid, and particularly at the user end. So we lose almost about 25% of the electricity in the conversion, inversion, and rectification. And that is why the thought of use of electricity directly at low voltage DC or DC came. And you are aware that many of the building management systems, many of the lifts, and many of our earlier DC systems in the cities will also use frequently, and even Calcutta and major cities had DC distribution. The distribution network in DC, even though the concept of LVDC is not so new, the discovery of electricity goes back to about 600 BC. The ancient Greek discovered rubbing fur on amber caused on attraction between the two, and so that Greeks discovered was actually static electricity. Since then, many brilliant minds, namely Franklin, Volta, and more have worked in the field of electricity. However, viable application of the electricity as technology came in 1831, when Michael Faraday created the electric dynamo, which solved the problem of generating electric current in an ongoing and practical way. This opened the door to the great American inventor, Thomas Alva Edison, and British scientist, Joseph Swan, who each invented the incandescent filament light bulb in their respective countries in 1878. Generation and distribution of electricity has come a long way. It was a direct current distributed power system which could serve only the needs of nearby customers. In those days, the power plants used to generate power in the range of 500 to 5,000 kilowatts. Later, American inventor and industrialist George Westinghouse purchased and developed Tesla's patented motor for generating alternating current. And the work of Westinghouse, Tesla, and others gradually convinced the American society that the future of electricity lay with AC rather than DC. This was the beginning of the technical contest between AC and DC. Today, after more than 100 years, we are at the crossroads of technological evolution. All these years, AC distribution system dominated the world to such an extent that it forced DC into wilderness. In India, we had DC distribution working in several cities like Kolkata, Kanpur, and Delhi. Till about 30 years back, DC fans of big size and even refrigerator was operating at many places in Kolkata. However, due to various factors, popularity and versatility of AC eventually outsmart DC to such an extent that DC systems had withdrawn completely. After a few decades of wilderness, DC system is bouncing back and forcing the mind of scientists, technologists, opinion makers, and all to see that what is the right kind of distribution system one should have. There are many arguments in favor of and against DC or AC. As this debate has been going on for quite some time, IC became seized with the matter at standard development and has become crucial for introduction of DC system back in distribution system. This matter would be deliberated by experts at length during the conference. I am pleased to inform that BIS has published the standard for guidelines for 48 volt ELVDC extra low voltage distribution system under IS 16711 2017. This standard covers the essential requirements for distribution of power from an extra low voltage 48 volt DC power source. This standard is also applicable to locations where electricity utility services are not available and power is derived from single or multiple renewable energy sources. India also holds the chair of Systems Committee on LVDC and IC, and really I compliment my team for being leaders in this field. I'm sure that this webinar would give the LVDC and renewable energy community as an opportunity to exchange views with experts and debate at length and pros and cons of LVDC distribution system to bring out the best solution for its society. With these few words, I appreciate the efforts of Bureau of Indian Standards and Center for Innovation in Science and Social Action, CISA, to promote the awareness and understanding of LVDC subject. And thank you all for participating in the webinar. My best wishes, and thank you so much.
Thank you very much, sir. As the chairman of ETD 50, I think a lot of responsibilities are there with you with respect to LVDC. Now we have the technical session. We welcome Sri Rajiv Sharma, Deputy Director General North and convener of Working Group 1 in IEC Systems Committee of LVDC for his session on a technical session on overview of LVDC and electricity access. Sri Rajiv Sharma is presently working as DDG North of BIS. He also worked in conformity assessment schemes, management systems, certification activities, as well as laboratory management and standards development work of BIS. So I would like to invite Sri Rajiv Sharma. Over to you, sir.
Thank you, Gopaji, for the excellent introduction. Now I'll try to share the slides, please.
Yes, your slides are visible.
Yeah. So good morning to all of you. As he told, my name is Rajiv and I'm presently posted in Chandigarh as Deputy Director General. But I also hold.
To make it full screen. Or not full screen.
Yeah, from my side it is full screen, but are you?
We are seeing not the full screen.
Should I try it once again?
Probably you can unshare and share the screen, not the window. Screen. Share the screen. You unshare. At the top, there is an arrow. There is the first is the leave button. Before that, there is a upward arrow. That is the share.
Yeah.
So you can unshare and share it again. Yes. Now, while sharing, you share it as a screen.
Is it better now?
Ah, perfect.
Okay. Yeah, so we start with something very elementary. What is AC and what is DC? AC, as you know, is a flow of electrons, to and fro motion of electrons, alternating at a particular frequency or number of cycles per second, and opposed to direct current, which is unidirectional, the electrons flow in one direction only. So this is the basic difference between what is an alternating current and what is a DC current. Yeah, this was discussed a while earlier. These two great personalities, they revolutionized the way the electricity was generated and distributed. Mr. Thomas Edison, he is a famous inventor known for several patents, but his one of the notable inventions was the light bulb in the year 1879, and he wanted this new invention to go to every household in USA. So he decided to have power plants. This is the first power plant which he built in Pearl Street of New York, and this used to generate power and used to supply to the households. The one big problem though was that the distribution could take place only about half a mile radius. So because it was a DC plant and it had limitations of supply distribution of about half a mile only, and this is how the network used to look like when he used to distribute the DC power to the various premises within the local area. And it was, of course, riddled with other maintenance issues and losses at that time. The other gentleman, of course, if you see on the screen, is Mr. Nikola Tesla. He came out with a unique solution, power generation and distribution through alternating current, and he overcome the problem of supplying electricity across long distances through the means of transforming it to a very high voltage and then through the distribution lines, transmission lines, and then taking the power to the places where it is required. So the generating stations, a step-up transformer, the transmission lines, which is the grid, and then at nearer to the places of use, it used to bring down to the lower voltages or the demand side voltages, and then it used to get distributed. This is how the electricity first started as DC, and then because of the rapid advancements in the alternating current space, it started progressing as an alternating current solution. But DC across this while did not lose its relevance. It continued to make slow inroads and steady progress in the entire space of DC of the electricity map. This is the stages of various progression of the electricity and the stage at which we are now. 1890 was basically dominated by, started with DC, but then AC and DC coexisted, and there were small power plants basically on the fossil fuels, and environment and energy efficiencies were not issues at that time. And across the century, the 20th century, the AC dominated the world and had large power plants. Again, the fossil fuel was the main supplier for the energy sources, and environment and energy efficiencies were again non-issues at that time. Just like DC was challenged by AC in the 1890s, now we are at a stage where the AC has once again been challenged by DC, and local small power plants have come up. Coal, oil, gas, wood, hydro, they are now considered as pollutants, and now the focus is on environment and energy efficiency. They have become the global agenda. And the top drivers for this are the use of solar photovoltaics, the battery storage systems, the lighting, and the other energy efficiency has become the main focus of the energy studies. And this is where the LVDC has gained relevance now. So if you just have a look around your room, we are already living in a DC world. All the things which we love and like run on DC. Take, for example, the lighting, which is mostly LED based, entertainment systems like music systems, the TV, the communication systems, the mobile phones, the computers, home appliances, maybe fans, refrigerators, air conditioners. They're all working on DC inverter technology, coupled with storage batteries and solar photovoltaic systems and so on. So we are all living in a DC world at the moment, already been discussed earlier. And going into the near future, this is also going to be a technology which is going to be revolutionized. The transportation system is mostly going to be electrified, basically through the DC. These not very far from now, this is going to be a new revolution which is going to invade all the society. Another issue is the last mile public installations. If you have a look around, most of them are working on DC because the entire internet connectivity, the electric mobile charging, the vehicle charging, the lighting, most of them are DC. This is one of the very interesting case scenarios which we came across. This is a greenhouse which is making ornamental flowers. The entire space is working on a DC. The solar panels on the top, the lighting systems, the air circulation, the water sprinkling systems, they're all DC based. In fact, there is no AC anywhere in this greenhouse which has been used, and it is an eco-friendly, renewable energy based, and the entire solution is DC. Of course, they have a AC incoming power, but that is a standby. In case something goes wrong, then they turn to that, but the entire ecosystem is DC based. So why are we talking of LVDC right now? Well understood, LED lighting, the IT, the multimedia, the consumer appliances, all of them are basically energy efficient, and the cost or the prices have come down drastically over the last decades. And the photovoltaic panels, the energy storage systems, the cost again has come down. Another application is electricity access, which I will discuss in the subsequent slides. This is also one of the main focus of the drivers for the LVDC advent. So now we are at the 2000s, where the focus has again gone to the DC environment. This has led the IEC. See, IEC was founded in the year 1906. It has more than 120 technical committees. And because most of the work was going on in the AC world, most of these technical committees are concentrating their efforts on standardization of the alternating current technology. Basically means generation, transmission, distribution, the safety and the utilization of all these aspects was basically concentrated on the alternating current technology. But with the advent of the new DC ecosystem has led IEC to develop a systems committee on LVDC with the main focus or the scope of standardization in the field of low voltage direct current in order to provide systems level standardization, coordination and guidance in the areas of LVDC and LVDC for electricity access. So the basic idea is to coordinate with the other technical committees at the systems level and provide guidance to those technical committees and other standards development groups, both inside and outside the IEC, on what interventions need to be done to promote DC in the standardization work. So the basic concept for the systems committee LVDC was to coordinate with the other technical committees. I strongly recommend that you visit the IEC page on the systems committee LVDC. There are a lot of interesting developments taking place. Mr. Vimal Mahendru, who's spearheading the activities at the systems committee, and he's at the helm of affairs, and he's taking keen initiatives. And there is a LinkedIn group which you can join, and there is an open forum which is very well active. So I strongly recommend that you have a look at the IEC webpage and also consider joining these social media platforms to know the latest developments on the subject. Another very interesting subject, which is a part of the systems committee LVDC, is the electricity access. And I happen to be associated with this working group, which is dealing with the electricity access. And the main task of this working group is to standardize the electricity access solutions. Have you ever wondered what this electricity access stands for? This phrase is quite intriguing. Electricity, of course, is very well understood, but what is access? What is access? What do you exactly mean by access? Access, what I understand, is some kind of a threshold or some kind of a hindrance or an obstacle which one must cross in order to get the privilege to use some basic thing like access control on the computer system or the biometric control or the access control in the airport. But what do we mean when we say electricity access? Is there a kind of a threshold which one must need to cross for the use of electricity? Most people in this group may not understand, and more so in the westernized societies or the developed countries, people will hardly realize because they are used to abundance and everything is available in plenty. The concept of electricity access is not very well conversant to them, but it is a reality. This is the fact that there are more than 1 billion people in this world who live without electricity. We talk of all the standardization, we talk of all the developments in the world, people getting economically uplifted by the governments, but the reality is that there are more than 1 billion people in this world who still do not have electricity in their houses. The reality is that 1 in 5 have no access to electricity and 2 in 5 have no access to the clean cooking. So this points to the urgency of the solution. We can't ignore all these facts. AC or DC, people are deprived of electricity, so they need to be given access. So they have to cross that threshold, and that too at an affordable price. Basically, these people, they are living at the bottom of a pyramid of development spectrum, and they do not come under the top priority list of the government spendings. And when we talk of the grid or the main supplier of electricity to the various parts of the country, they will still have to wait for a little longer so to have the electricity in their houses. But with the advent of the LVDC concept and with the new ecosystem of the DC appliances and generation systems, there is a convergence of technology which enables them to leapfrog from what they would have had after several years. The technology permits. With the convergence of these technologies, it is possible to have basic electricity in their households right now. So it's a leapfrog. They don't have to wait for several years for the electricity to reach their houses. Energy is a golden thread that connects economic growth. Most of you will agree with me that energy poverty is equal to economic poverty. If we want the people in the country to develop, we have to provide energy. We have to provide energy sources. Electricity is the main energy source which is required for the economic development and upliftment of the people. So energy is a definite requirement for the people for the economic development. This has been brought out by the global goals for the sustainable development brought out by the UN. There are 17 SDGs, and it was well understood that there is an importance for energy, and therefore affordable and clean energy is one of the sustainable development goals which each government in the world seeks to address through these SDGs. It is a very important aspect. If we want the people, the status of the people in the country to improve the economic upliftment of the people, we have to cater to the affordable and clean energy SDG. Simultaneously, the World Bank, through their SMAP multi-tier framework, they have also come out with a study on what basically the electricity access means. It is not a question of yes or no, either the electricity is available or not. Even if it is available, it is not available all the time. So they have classified the entire area of electricity access into 5 tiers. Tier 5 basically means abundance. Everything is there. Electricity is available most of the time, and for most of the applications for which electricity is required. So tier 5, it's an ideal situation which definitely everybody would aim for. But that is not the case. There are other tiers, tier 1, 2, 3, 4, and 5 in the increasing order of the availability of electricity. This is how the World Bank sees the entire issue of electricity access, and this is how it is aimed to address. When the governments look at this situation, they at least feel that tier 2 or tier 3 is the most is the basic requirement which every person in the country should be able to access. So the standardization space looks at these 2 tiers which basically mean light bulb and a few comfort appliances within the household for maybe a limited number of hours in a day to enable the persons to have a comfortable living and to improve the quality of their life. So the entire focus of standardization in our working group related to the electricity access is to create a solution which provides electricity access to the people in the tier 2 and tier 3 framework of this SMAP system. BIS again understood the relevance and importance of the activity, and the ETD 50 committee constituted for LVDC power distribution systems. Mr. Soda is at the helm of affairs in this sectional committee, and the scope of this technical committee is also to have system requirements for safety and installation guidelines and LVDC products, including electrical wiring accessories and applications, integration of DC infrastructure, non-traditional distribution network microgrids. This is the scope of the ETD 50 BIS sectional committee on LVDC. As I told you, Mr. Soda is the chairman of this technical committee, but there are other experts representing the various stakeholders, the regulators, the government bodies, the academia, research organizations. BIS is a member secretary in this, public sector companies, industries organizations, testing laboratories, consumer groups, private sector industry, solar and wind generation. They are all the stakeholders, and they are very important members. They contribute effectively in this, the working of this technical committee. This is the standard which has been published and which Mr. Soda also referred to. It's a 48 volt extra low voltage DC distribution systems, which has been formulated. Basically, it has several considerations. See, the standardization basically seems to basically implies that we must identify all the issues related to the concept and provide solutions which are affordable, which are convenient, which everybody has the access and the right to use. So we understand that they are going to be the first time users. They have never had the access earlier. So the safety becomes a primary concern. So we have to understand the requirements of safety, the dimensional requirements, and the maximum, the effort, the use of the components to make a solution which is affordable. So the solution which we provide has to be not only safe and durable, it has to be efficient, it has to be scalable, because later the requirements will increase and the persons who are living with this support system will have higher requirements of power, and the system itself has to be upgraded and scaled up. So the basic idea for the distribution of electricity, the standard on electricity access was to define the voltage which is safe, have the dimensional compatibility, leverage the existing AC components, because already they are wired up for some kind of AC usage. So we have to take maximum usage of those components, the grounding considerations, the earthing, coexistence with the AC grid, and compliant with the existing standards, and evolve into a microgrid standard in the future, and ensure scalability and a sustainable ecosystem of parts and suppliers. So 48 volts was chosen as the primary voltage as it is considered extra low voltage. There are no electricity hazard issues associated with this, no question of shock due to the electrical power. This is what made it most convenient voltage, and due to the loss considerations, this stands out to be an optimum voltage systems. These are the kind of households which have benefited or where the standard is aimed at. See, again, as I told you, that the grid possibly will not reach anytime soon to these locations, and the government priority does not permit expenditure to the level that the grid reaches there in due course in the near future. So the electricity access standard, the 48 volt standard which we are talking about in India, and also a parallel standard which we are developing at the IEC Systems Committee LVDC in the working group, which caters to the tier 2 and tier 3 of the SPAP multi-tier framework, provides solution to households like these who are remotely located They are not going to get the convenience of a grid electricity. So they have to struggle to have access to electricity. So providing an affordable solution which is safe, reliable, this is the concept, and this is the work which we are presently doing in the working group 1. The far off locations. See, consider these. When we talk of standards, it has to benefit the people. And it has to benefit the people so that the quality of the life improves. And the basic purpose of standardization here is, and my message to you all is, that standards are everywhere. Only we fail to see their importance, and we don't recognize that how important they are till something goes wrong. See, the standards are formulated by experts who represent the various stakeholders. And it is our duty, and it is our moral obligation to the development of the nation to develop standards which actually benefit the end users, the people who require such kind of solutions from us. And it is our responsibility to uplift the quality of the life of the individuals and to provide them with a comfortable environment, maybe at whatever locations they are. They have the right to these privileges. So it can't be considered as an access issue. We have to give them access. We have to give them unrestricted, at least the privilege of having the basic amenities which electricity brings with it, decent livelihood and comfortable living. These are the standardized practices. They have been also upheld by the Ministry of Power and Government of India. This is the solution which has been very well laid down, and all the safety considerations and all the basic parameters have all been written down in the standard. I recommend that you all have a look at the standard which has been developed. In conclusion, these are the basic concepts. LVDC is happening, and it will touch all our areas of electricity. LVDC standardization work has commenced, especially the electricity access, and it makes sense for developing and developed countries both. And I strongly recommend that all of you who are technical experts on the subject, even the related subjects, take active part in standardization work. How you can involve yourself in standardization is through various means. All the things are now, systems are all online. You can contribute by way of making comments to the existing standards. Maybe you can propose new subjects for standardization, and maybe also you can join the technical committees as technical experts and give your opinions in the technical. The basic idea is to get involved, make difference to the lives of the people who really need these standards, and very importantly, bring a smile on their face. Thank you so much.
So thank you very much, Sri Rajiv Sharma. We are overshooting about 15 minutes, but however, it was a very interesting presentation, sir. Thank you very much again. Now we welcome Sri Vimal Mahindru, President of Messrs. Legrand India, for a session on international standardization in LVDC. Sri Vimal Mahindru is presently the IEC Standardization Management Board alternate member from India. He has been a member since January 2015. From 2017, he is the chairman of the IEC Systems Committee on LVDC and LVDC for Electrical Access, SYNC LVDC. He is also presently convener of Council Board Task Force on Steering Global Standardization to address UN Sustainable Development Goals. As Sri Rajiv Sharma told, there are 17 Sustainable Development Goals. He is also the IEC ambassador, especially focusing on sustainability agenda and guiding IEC's deployment of SDG-centric standardization and conformity assessment programs. So we welcome Sri Vimal Mahindru. Over to you, sir.
Thank you very much. I trust you can hear me loud and clear.
Yes.
Wonderful. First of all, hearty welcome and namaste to everyone who's on this conference. I hope you are all safe and well. I'm indeed honored to be part of this webinar, to be speaking in the same platform where Soda ji and Jayant ji, Preeti ji and Rajiv have already spoken. It's a tough act to follow, but let me try and connect somewhat with what Rajiv mentioned in his slides on SDG and start from there. We all know that there are 17 SDGs. These are the Sustainable Development Goals, which are more like promises, fundamental promises made by governments to their citizens. Our Honorable Prime Minister was one of the first signatories to these goals in 2015 in Paris, what is famously known as the Paris Accord. And we made these 17 pledges to all the citizens in our country. In this process, at the IEC, the organization that I'm deeply engaged with, did a survey to check how many of these 17 goals are actually impacted by electricity or the absence of it. And we recognized, much to our own surprise, the huge challenge that we have. All 17 of these SDGs are directly impacted by electricity or its absence. For example, we can talk of good health and well-being, but for good health and well-being, the world is today realizing painfully that we need vaccines, and vaccines can only be transported if they are refrigerated. And refrigeration today requires electricity. And like this, if you can go for education. Today, education is not just about books. It's about remote learning. This conference, where we are sharing knowledge and information and exchanging ideas, it's through electronics and communication, all of it running on electricity. Like this, if all the 17 SDGs are impacted by electricity. The biggest challenge of all this is the world does not have 50 years to do this. We have to accomplish all this by 2030. And so that's why this time, this very decade we are living in is known as the decade of action. The UN has declared this as the decade of action. And the new IEC strategy for global standardization of all electrotechnology work is actually dovetailed with this SDG strategy. So IEC also is having a strategy now, which is just formulating, which is going to be implemented from 1st January 2022, dovetailing exactly with this and implemented completely between now and 2030. Let me also connect with the slide that Rajiv ji shared about DC. He showed a curve that the sinusoidal wave was AC, and in the DC world, it is a straight line. But let me challenge this very concept also. While I agree with this, but if you think about it, this is also DC. This is also DC. So is this, and so is this. Anything which is unidirectional is DC. That was the traditional definition, which was this first curve that I showed. But all of the other curves are today possible thanks to electronics. And because of electronics, we are kind of playing with all kinds of waveforms. And what's emerging is not just AC or DC, but DC. The concept of DC itself is evolving to digital electricity, where even a pulse, a unidirectional flow of electrons, but as a pulse, is also seen as DC. But there are no definitions for this. So one of the first work that we have to do is actually create the right definitions for direct current. For this purpose, at the IEC in 2017, the System Committee Low Voltage Direct Current and LVDC for Electricity Access was formed. I have the privilege of chairing this committee since its inception, and Rajiv ji and I work closely on the electricity access part of this committee. This committee today is having about 30 members, and if you can recognize the flags on screen, majority of these are developed countries. Now, you would wonder why are they involved in this, because electricity access is a challenge for developing economies. The real reason is that DC is kind of everywhere. Rajiv ji very beautifully explained that almost anything and everything we do today is using electricity and its consumption of electricity, which is more in the form of DC. So all these countries are trying to reduce their carbon footprints, trying to meet their commitments for carbon reduction, reduction of dependence on fossil fuels, etc. So that's why this deep interest in this work. I'm not going to go into details of this slide, but at the same time, the key is that there is a lot of work happening. The box in the yellow is an important aspect of the standardization work. This is where we are looking at all the definitions and the basic fundamental details of direct current. Because when AC came in, and over the last 100 years or so, we've kind of perfected the science, the technology, and standards around alternating current. But DC was kind of laid aside. It's now that the work is starting on DC standardization. And that's why I encourage you, as Rajiv ji also mentioned, this LinkedIn group. There are today about 850 members from all over the world, and they are thinkers purely on DC, right from students, research associates, manufacturers, and regulators, economists, etc., who are purely thinking of direct current and how it can impact the coming world. And so I encourage you to look at this group. This is a list of all the activities which are right now going on in IEC on electricity access and on standardization of direct current. I'm not going to go into all of these, but these slides will all be available. So from this slide deck, you will be able to understand which way the world is moving and what are those areas of interest for you, which you may want to get involved with. But more importantly, while we have started this work on DC standardization, there is a huge amount of gap. You can see from this list that there is so much of gap between the demand for direct current and direct current standardization worldwide that we are actually falling short of even experts who can get involved with this work. For example, if you see DC consumption and DC consumption metering, that's a gap. Segregation of AC and DC circuits, even the basics on how you will code the wires, the plugs in sockets, etc., is not there. And so this is the direction that the world is moving in, and we need to kind of look at some of these issues in a bigger way. I mentioned that JWG9, which is a joint working group of the system committee and an IEC committee called TC8, the technical committee 8, these are the kind of things that we are looking at. And you can imagine this is the fundamentals, or let's say the basic building blocks on which rest of the standardization around DC will work. This group has already published one technical report, which is TR 63282, and I'm sure it is available on the IEC platform. It talks about a lot of important aspects for DC, especially about DC voltage bands. What are those bands which we can work with? In AC, it's very common to talk about 220 volts, and there is a band around 220 volts. Kind of, we don't even look at appliances when we go to buy. We know that it will be somewhere in that voltage band. But in DC, there is no such band which has yet been standardized. So this is one of the work that is going on. It's obvious that 48 volts is one of those bands which is emerging, but there are other DC categories also for higher loads which are being standardized. So I encourage you to look at this standard from IEC, which is coming up. It's already available on the IEC platform. So those who are interested and those who really want to look at the way this is going and perhaps develop their own products or solutions around DC on this, they may want to look at this product. This is some of the future work. Of course, they're going to upgrade the existing standard also, but also look at power quality issues. So in AC, we have looked at power quality over a long period because it's been around for quite some time. But in DC, there's hardly anything available. For example, electromagnetic interference. We don't really know much about it, let alone create standards. But we know that we see interference all the time when we use our mobile phones or when there is bad weather. Our TV receivers stop getting the signal. So we really need to see what's going on, bring information to the IEC platform so that the right standards are made available. Rajiv ji has already spoken of this. Tier 2 and 3 is where the current work is happening in IEC on electricity access. Tier 2 and 3, as is shown on the screen, is about giving 4 to 8 hours of electricity, typically starting in the morning and evening hours, but also because it is 8 hours extending a little later into the night or in the afternoon if you need it in the kitchen for simple appliances. The SMAP World Bank multi-tier framework is very well explained on this website, which is the link is embedded here, so you can just get this information from World Bank. And we have taken in IEC the World Bank framework and built the standards around it. The basic benefit of doing this is that World Bank is funding a lot of electrification programs worldwide, especially in Africa and Asia. And for all these programs, it's easier for the donor and the donees to both look at IEC standards for implementation of electricity access programs. Another interesting work that's taking place in IEC is this on predicting electrical compatibility. We all have seen instances when we wanted to charge our laptop from a USB connector, but it didn't charge, but it charged our mobile phones. The power requirements, voltage requirements, etc. are different, but the physical connectors many times are same. And this gives the illusion to the consumers that anything connected to anything through the same USB-C or similar connectors should work. Of course, it doesn't work. But how do you take this information to the rural interiors where the knowledge or education may not be there? And unfortunately, this problem is rampant the moment you get away from urban centers. In Africa, there are horror stories of people connecting the wrong loads to the power sources or batteries just because the plug and socket was compatible, and it created a huge fire and fatalities. And so to avoid those kind of things, there is this program that we are trying to do in IEC. This is at the early stages, but it's an important work that is happening. But another very interesting evolution which is happening in IEC is standardization for Industry 4.0. Now, for Industry 4.0 is almost entirely about electronics and robotics and artificial intelligence, machine learning coming onto the shop floors. All these phrases that I'm mentioning require direct current. If you look at this picture on the screen of a manufacturing shop floor for cars, even the belt is moving with DC drives. The robots 100% work on direct current. So if there is so much of consumption of DC on the shop floor, don't be surprised that shop floors of the future will actually be predominantly DC, and there may not be any need for any manufacturing shop floors to have alternating current. Rajiv ji mentioned briefly this use case, which is of the public last mile. This is the outdoor grids, which is not inside the building, but outside of building, but there is still a lot of power consumption. Street lights, traffic lights, fountains, public parks, a lot of them requiring electricity. This use case is very common in India, but unfortunately, there are no international standards. And I'm not sure if there are any people from the city municipal corporations here. You will find that as a result, every utility or city council is having its own specifications, thereby leading to some kind of variance from one to the other. This needs to change. And I think for this purpose at the IEC, we are developing a standard for this kind of work. Just a quick news on standardization work across the world that is happening. In Europe and UK, there is a lot of effort going on. This is just for those who are interested. In Canada, there is some work beginning on DC microgrids, which are inside the buildings. So not just for electricity access, but these are high-rise buildings, big buildings, lot of loads. But imagine the entire inside of the building is going to be DC. In UK, there is a new standard being developed called the Future Homes Standard. This work started in 2019, and because of the pandemic, it got slowed. It's again coming up. And with the loads changing, instead of us getting gasoline into our cars, because we are putting electricity, the load is coming onto the homes. So how are the homes of the future going to be designed and configured for electricity, which means again DC? That's the work that's happening in UK. This is just a picture of the last face-to-face meeting we had. This was in Amsterdam, where the group met for a conference at a university, where we invited folks from all over the world to speak on DC and which way the evolution is. I am convinced that the world is moving toward DC in a big way. It is only a matter of time and perhaps positioning of DC vis-a-vis AC, developing the right transition journey. Of course, there is so much invested by the world in AC that we cannot pull out AC and just replace it with DC. That would be a huge cost to society. But making the right transition would be important. At the IEC, we try and make a difference to the community by doing the right things. This is a picture from Australia, where you may know that recently there were big fires. Now, Australia is really looking at direct current in DC microgrids to isolate sections of the grid where there may be fires and so a fire hazard, but rest of the communities can continue to receive electricity. So there are multiple new ways of looking at current. In fact, I these days struggle to think of a use case or an application which is strictly alternating current, and it cannot be done in DC in a more efficient way. That's the kind of change that we see. I'm giving here a lot of links to technology papers and work done by the IEC. There's also a TED talk on LVDC, which may be interesting for some of you. And with that, thank you very much and appreciate the time and time for this. I'm not sure, I think I took a little longer than I was planning to.
Yes. Thank you very much, sir.
Thank you.
We are a little bit over time, but that's not an issue. We have a question and answer session, but so far there were no questions, so we can very well manage the time. So it's a great pleasure for actually all India to see that India is leading the global standardization on LVDC. Actually, this gives a great opportunity for Indian companies to become global leaders, and as well as a lot of new employment opportunities, provided we do our responsibilities properly, especially in the field of R&D and the development of new products and so on. And if we can push for some kind of funding from the government for the investment, that would be really great. So thank you very much, sir. So now we would we welcome Sri Rajesh Kunnath, founder of Radio Studio in Chennai. Mr. Rajesh Kunnath is the founder of Radio Studio, a design service and products company based out of Chennai. He is a hardware engineer with hands-on experience covering multiple domains of from design to power supplies to embedded system and RF microwave design. He is a committee member of IS 16711, the extra LVDC distribution system. So over to you, Sri Rajesh Kundath. You have to unmute.
Yeah, are you able to hear me?
Yes.
So I am making this presentation from, from my parents' village in Kerala, and here, we do have frequent power cuts. And do you know how, I'm going to go through the presentation even if there are power cuts? It's going to be using DC storage. I have a DC storage on my router. I have DC storage on my laptop. And the only thing is that this storage is not standardized. So here is a live use case wherein a standardization of DC storage can bring about immense benefits. Especially when it comes to reaching economies of scale, where the cost of storage will come down drastically. So having said that, I will just start my talk on the Indian DC standard. I'll just let me just open the. Are you able to see this? Hello?
Not yet. Not yet.
Are you able? Huh?
Not yet. I think you have shared the screen. It's coming.
1 minute. Let me see how to.
On the top side, there is an.
Yeah, I have. Okay. Yeah. Is it okay now?
Yes.
Okay, so yeah, so I'll be basically limiting my discussion to the specific aspects of the standard. And if you have any questions, please don't hesitate to ask. So in fact, it's one of these standards wherein India actually spearheaded, the standardization work. In fact, the BIS actually released the standard much before IEC or IEEE could take note of it. And in some sense, there was an element of surprise, at IEC and IEEE that we went ahead and did this. And, both at IEC and at IEEE, I think, this basic version of standard has gone through what I would say greater refinement. So what will happen is that this standard would again, would have the opportunity to be revised based on the refinement that is happening at the worldwide standardization endeavors. So this is a standard for India, and it's developed by BIS. The other aspect is that there's already several thousand installations that have already been done on the standard. My friend Venkat Rajaraman will actually be covering some of these aspects of the installations in this forthcoming talk after I finish. And what we have tried to do, as part of the standard development is, to take, some of the issues pertaining to India, considering that, we need to create solutions that are reasonably priced, even, at low volumes. And how do we ensure that, we are able to use whatever is available on the AC ecosystem and incorporate it into the standardization activity. And of course, if there is a possibility of adoption of the standard throughout India, this is going to help us with the uptake of distributed renewables. Most of the renewables that when we talk about renewable energy, it is actually centralized renewable energy. What I mean by this is that we essentially have large solar power plants in the megawatt or the gigawatt capacities, and these are basically connected to the grid. But with distributed renewables, we are looking at a totally different scenario, wherein we have small houses being powered with small solar panels, which are completely independent of each other. And once this ecosystem comes into picture, there are several other things that can happen, like how do you interconnect them, how do you ensure that there is sharing of electricity, etc. So once we have an uptake of distributed renewables, we have a lot of challenging technical things that can come for that can happen in the future. So the standard per se, the priority was electricity access. And what do you mean by electricity access? Rajiv Sharma has described it in great detail. So I will not get into that. Okay. From this standardization perspective, we were looking at safety as our first priority, because if we look at those people who haven't had access to electricity yet, they wouldn't understand the safety aspects of electricity. So the first consideration was that it should be absolutely safe, even for first-time users of electricity, and it should be scalable. And we should have some rules wherein in areas where there's no AC grid, and eventually when the grid is extended, which will happen, right? How do we peacefully ensure that that is also possible to be integrated? So these are some of the things that the Indian standard actually looks into, which the international standardization has not yet considered, because they fear for a lot of other safety related issues. So this is essentially the same thing that I mentioned. So the first thing that we need to fix upon is what should be the choice of voltage that has to be used. And we cannot just pick up an arbitrary voltage, because there are voltages that are defined by the IEC, and we need to choose only from those voltages that are already approved. And then the second thing is, once we choose this voltage, then automatically what are all the safety issues associated with that voltage? So one of the things about voltage is that there is something called an SCLV voltage range, which is the safety extra voltage, which is any voltage under 60 volts is supposed to be termed as a safety extra low voltage. And when we choose a voltage that falls under this category, then we are looking at there's a lot of things that was already defined. And one of the things is that most use cases, safety is guaranteed. So that's one of the reasons why we chose 48 volts. We need, there's always this conflicting requirement of having a higher voltage, because it will reduce current requirements and attendant I²R losses during distribution, and safety. So the thing is that if we go beyond 60 volts, then we are looking into a scenario where the cost that is needed to put in the safety ecosystem would be prohibitive. So that's the reason why we chose 48 volts. There have been a lot of discussions, both in internal BIS as well as internationally about 48 volts. And now I think that it's almost accepted, that 48 volts is a good voltage for DC distribution. This was not the case a few years back, but now I think every international standardization organization, accepts that 48 volts is a good voltage to go with. Now, what are the specifics of this standard? So this is essentially, we call this as a distribution standard. So what this means is that right now, if you look at the AC distribution in your premises, you will have a 230 volts, either a single phase or a three phase coming into the home, and from there, it goes into a distribution box, and you might have, and as part of the distribution box, multiple MCBs. These are the different circuits that are derived from that single incoming feeder, and each of these are protected with a fuse right at the inlet. And there's there might also be an earth leakage circuit breaker. So if there is any issue with earthing, the earth leakage circuit breaker will go off. So similar to that, we envisioned, is there a way in which we can come up with a scheme wherein we have a DC distribution which is very, kind of mimicking the AC distribution. So, so what we have done is we have created something very similar to an AC distribution. So here you'll have a DC distribution box, and you will have again multiple circuits, and each of these circuits, will have a 5 ampere current limit. So the initial standard, we have not really limited, on the number of circuits, but there could be some limitation that is coming, in future, because the feeder line might need some, current restriction, etc. And the standard also looks at things like, what should be the size of the conductors that we are going to use. And here again, the intent was to use, the wiring conductors that are used in AC, which is 1.5 square mm, 2.5 square mm, 4 square mm. The reason why, we would have to have multiple, sizes is essentially because, we want to ensure that the I square R losses are minimized. The voltage drop is also minimized from the start to the end of the distribution. There's also, some inclusion of the coexistence with AC. That is, eventually when AC comes in, how are we going to connect those as well? So when it comes to safety, how does, what kind of safety measures are we looking at when we look at an SDLV distribution, right? The SDLV, the safety, extra low voltage, is essentially a floating output voltage, right? In order to give you an analogy of what this means, if you take your charger, for instance, the laptop charger, which many of you are familiar with, and those chargers will actually have, depending upon the model, the voltages will vary from from about 11 volts all the way up to 20, close to 24 volts, and they have a positive and negative, which is which has nothing to do with ground. So the way this supply is derived is by using what is called as an isolating switch mode power supply, which takes in a 230 volts input, but there is really no electrical connection between the input and the output. So this is done by using a switching transformer, and the coupling is entirely magnetic. So the voltage that is derived from what is called as a class 1 power supply that is used in these chargers have a differential voltage of 24 volts or 11 volts across them, but it is not related to any of the voltages at the incoming. So even the earth it is isolated from the earth as well. So that is why we get safety inherent in a CLV output, and that's the same concept that we are using on this when we recommend this power supply as well. We are saying that the 48 volts derived shall not have any it's going to be completely isolated from earth. So if you're going to have an installation that is from a PV panel, the positive and negative will be coming directly from the panel, and there will not be any connection to earth. And it's actually a similar case if you use a battery as well, right? So if you use a battery, you will have isolated voltage from its terminals. And the only issue with batteries is that they are possible, they can supply extraordinarily high currents. And it creates two things. It can cause arcing as well as fire. So the way in which we have addressed both arcing and fire is that if you are going to use only 5, if you are going to have a maximum of 5 amps per circuit on a 48 volt system, there is going to be arcing, but the arc does not sustain. It will, the arc will be quenched. In higher voltage DC systems, this is a huge problem, unlike AC systems, wherein AC systems go through a zero, which actually automatically quenches the arc. But in a DC system, if you're looking at a 330 volt or 450 volt AC system, a 450 volt DC system, the arc will travel. And so therefore, all these, standards or all these areas which use high voltage DC, there has to be special ways in which arcing has to be identified and suppressed. Whereas in voltages up to 60 volts, it's not a problem. And there have been a lot of studies done at 48 volts as well, that 5 amperes at 48 volts does not lead to a case where an arc is going to propagate. So from a technical perspective, what we call this system is an IT system. This is in contrast to the DC the DC distribution which uses TT system. It's essentially an isolated system is what we are referring to. So there is what I'm trying to say is that this system of grounding is not different from from what IEC has already included in their standards. So if you look at IEC 60364-1, this is very well illustrated. So when I talk about 48 volts, I normally I get asked a lot of questions. So one of the things is, what happens to, if you're going to standardize on 48 volts, what will happen to the existing 12 volts and 24 volt DC products that are available? So you can still use those products. It would need a DC to DC converter to be, to be used. And what I'm seeing is that the cost of DC to DC converters are coming down like anything. And with the standardization of USB-C, we will see even more, greater variability in terms of DC to DC conversion, and with an attendant decrease in cost. Then the other thing that I get asked is 48 volts safe under all environments? The answer to that is 48 volts is not safe under all environments. It can be, users might experience a mild shock, especially in damp environments. But unless both the user comes into contact with both positive and negative, it's very difficult for any chance of getting electrocuted or even experiencing a mild shock. And then the other thing is arcing. Arcing is well understood phenomenon in DC, and this is it doesn't go away. But the fact is that by limiting the current and the power that is available in the system, we are ensuring that the possibility for arc to propagate is just not there. So what happens is that when there is, let's say, there's a small insulation fault, you cut the wire and then you bring two wires together, there is going to be an arc. But as you separate it, so what happens when arc has sufficient energy to propagate is that it's now able to melt the insulation and go and pass over the the insulation. But what happens in the case of AC is that it will we found that with these limited powers, it cannot propagate continuously. And there have been research papers that has vindicated our approach. So arcing is not an issue. So what are the next steps? We are already in the process of mooting an international standard with IEC and IEEE. And what we are really looking for is to have greater industry participation. There's also a big need for a plug-and socket, a DC plug-and socket for 48 volts. So that's something that is still being discussed. Then we need to create a 48 volt ecosystem, supply chain capacity building, and and then there are a lot of other things, with regard to standardization, bringing in, smarts into the mix. How do we, scale the system for energy sharing? How do we, have put IoT in place so that energy is optimally shared? How do we maximize energy efficiency? So all these standards don't talk about energy efficiency, but energy efficiency is another big thing which can come in if we also include IoT and stuff like that. And then the next thing is, what is the next higher voltage and how do we take care of it? So that's it. Thanks for listening. Hello?
So,
yeah.
Yes, that's actually a wonderful presentation, Mr. Rajesh. And belated Onam wishes to you and your family on behalf of all participants. We have a
Thank you so much.
Yeah, approximately 350 plus for the last almost 1 hour. That's actually a great number. Now we welcome Sri Shashidhar Rayasam, GM, General Manager R&D of Signi Energy Limited for his paper on LVDC. Powering the last mile challenges and opportunities in implementation. Sri Shashidhar is the R&D General Manager of Signi Energy. He has got over 20 years of experience in design and development of products for telecom, infra and power sector. He was associated in the past with Energy Astra Limited, CMC and the ICSA India Limited in various senior technical positions. Shashi has a BTech degree in electrical and electronics engineering. Over to you, Mr. Shashi. You have to unmute yourself.
Yeah.
Not
Hello.
yet.
Good afternoon.
Yeah. That's clear.
Yeah. Thank you. Thank you, Mr. Gopal. So I am audible?
Yes.
Oh, thank you. Good afternoon, one and all, to the dignitaries, eminent speakers, and audience. So I am going to present my screen.
You have to make it full screen.
Yeah, one. Yeah.
That's perfect.
Is it visible?
Perfect.
Right. Good afternoon. So I am going to talk about the challenges of this last mile connectivity for the LVDC, and today I am going to give you a practical scenarios where we have faced this challenge in the last few years. To start with, I think Signi Energy as a company, we started our journey in 2014. The company was incorporated in 2014 with it, as an incubated company with IIT Madras and working on a specific technology called solar DC. So the solar DC is, something to do with the same low voltage DC supply, and this was basically to provide energy access to a lot of unprivileged, areas or people who did not have access to clean energy and affordable energy. So as I think other eminent speakers have given their views on this particular thing, it is the same, the SDGs, the Sustainable Development Goals of UN, which talks about affordable and clean energy, and where there is a goal also to ensure the access to affordable and reliable energy for all by 2030. So we embarked on this journey from 2014. And what we have developed, maybe I think most of these slides would be repeating what other speakers have presented. But as you can see, I think this is the area where we are working on tier 2 and the tier 3. But what Signi as a company we have tried is tried to see what would a tier 4 or a tier 5 look like. We have developed some products and we try to deploy them at customer places to understand how would be the feedback and what sort of a response would that be. So yeah, why LVDC and why now? As you have already heard that there is a significant cost reduction in devices. There is a significant cost reduction in the storage appliances and power sources, basically like PV panels and batteries that can store the energy. The efficiency of these devices have increased enormously by getting powered through DC instead of AC. And there is a motive also for this particular LVDC to sustain in the market. So this is our way of seeing this particular why LVDC. So if we imagine about 10 to 15 years back, we hardly heard about DC appliances. DC appliances were mostly the emergency bulb that used to work at our homes, the emergency lights, or some portable fan which can operate on battery. But what happens to the other appliances? So as the electronics market improved, the electronics market grew, and the BLDC motors and other things came into picture. We thought there is a need for the basic DC technology to be upgraded slightly, and then add power electronics into this particular thing, give some sort of intelligence, smartness to this particular segment, and then cater to a larger market. And that's where we saw this opportunity or the market gap from between about 50 watt small appliances and above the 10 kilowatts. There are already AC microgrids which are available. But what happens to this band between 50 and 10 kilowatts, 50 watts to the 10 kilowatts, is where we targeted. And during our journey, we could actually do all these things, like we powered a refrigerator on 48 volts DC. We have chillers and freezers that work on 48 volts DC. We integrated power looms on 48 volts DC. And the induction stove also was made on 48 volts DC. So there are a lot of advancements that happened in this particular area, and necessarily the energy access to be given to the underprivileged people is a reality. I think we can provide that access to the energy to the remote areas. Again, a similar slide. And what are the key market drivers for this particular? The energy, the developed economies probably will look at only the energy efficiency. They may not have the access challenges, but they can improve the efficiency in terms of energy. And for the developing economies, as we can see from this map, pretty much a larger amount of the world is still, not having access to a clean and clean energy for that matter. Yeah. So this standard for LVDC, as Shri Mahendraji and Raji mentioned, this is IS 16711. We have been closely working with BIS to understand this particular standard and we have implemented these standards also in our products. So the standards typically talk about the choice of voltage, the safety features, and all these aspects. So the priorities and considerations also Shri has also deliberated on this particular topic. The priorities are there. The people who do not have access to energy today, the DC system can work fine. But what happens when an AC grid comes into their area? So the standard even takes care of integrating AC with these systems and have a coexistence of both AC and the DC. And when we were working in this particular thing, we even got many inquiries from urban markets where people do not have really a challenge of electricity access, but still they wanted to have the solar DC or the LVDC to be implemented in their household. And even some people want to build their entire homes on LVDC because now there is no dearth of appliances running on DC. Maybe 10, 15 years back, we may not have many DC-based appliances, but today we have a lot of DC-based appliances. And the technology has also matured to a stage where 48 volts DC can provide power to a lot of these appliances. Yeah, and the safety factors and other things like Shri Rajesh Purnarji was also mentioning. A lot of safety is there with this safety extra low voltage systems under 60 volts. Anything that works under 60 volts DC. Today we operate batteries, we manufacture batteries, we use them on our work table, and we touch them barehanded. This is not the case with a 230 volts AC, where there is a hazard of electric shock. But with the DC systems, absolutely it is as good as you touch your mobile chargers every day. You touch your the mobile charge output, which is a 5 volt DC coming out, you touch with your bare hand, you don't feel anything at all. So same is the case with voltages up to 60 volts DC. And we have deployed close to about 45,000 installations in the states of Assam, Rajasthan, Manipur, Jammu and Kashmir, and Meghalaya. So most of these installations were in remote locations. If you see at this particular picture, the batteries are here underneath, which weigh about 32 kgs. So just the weight of the batteries itself is about 32 kgs. So this was our first generation products that were deployed. And the challenges related to the last mile connectivity, yes, these are the practical last mile connectivity challenges that we have faced. To power up a hamlet of homes on a remote island, essentially the devices need to be ferried on boats, on something like it across the river to reach there and then deploy them over there. And as I told you, each battery weighing about 32 kgs, managing the weight is also a big challenge. And when you are taking material boats and ferries across the river, due care has to be taken in terms of handling this particular material. And when it comes to the last mile connectivity, there will not be any professional courier services. It would be the local people who will help, who are not trained to handle such devices, but they just put it as a heavy equipment inside the required place. So the access to the last mile connectivity is also very poor. The roads are not built properly. There are waterlogged areas everywhere. Once there is a heavy rain, you cannot even find where the land is and where the water is. And no motorable roads to reach the end consumer. As you can see in these images also, there are some huts in such areas where a motor car cannot, a motor vehicle cannot even reach in that particular area. So all these means of transport like bullock carts, boats, people carrying it on their shoulders. So this is the kind of approach that we need to have to power up those remote areas or those areas where access to the energy is not there. So this is one of the Manipur where we have deployed. It's a hilly terrain and people have to just carry it on their backpacks solar panels. Imagine 200 watts or 250 watts of solar panel, 32 kgs of lead acid batteries on their back. So what we did basically to address some of these challenges were we need to we have taken advantage of technology, migrated from lead acid batteries into lithium-ion batteries. So where the battery was weighing about 32 kgs in the first case with a lead acid battery, the same capacity of battery we could do it in about 6 to 7 kgs. So that's how we kind of addressed some of these pain points. So the more challenges what we need to address here is how to make the products more portable and how to provide the end user products which are more easy to use. So today with technology, the challenge is technology provides us a lot of means to use new things, but managing technology is still difficult in this modern world. Even today, when we have some glitch with our internet connectivity or probably with our a web call or something, we still struggle. We have the still we are not able to figure out like how to fix that particular problem. We struggle sometimes to do even some technical things. So think about people who really are not aware of these technologies, people who are just living in some forest, some hilltop, who have not undergone any formal education or training or any such knowledge on technological aspects. When they were given a device to operate, which can power up their home, how do they use it with a simple, much less effort? How can they intuitively understand how this works and how to turn it on, how to turn it off? So these are some of the things from a product perspective. I think from a technology and product perspective, one needs to think in terms of developing the product. Similarly, on serviceability and repairability and such aspects also, how to provide service to such customers, providing toll-free numbers, because having a service center in every remote location is not possible. So helping them over a call on how to reset their device, or probably how to again bring up their device just in case it is off because of any reason. So these are some of the challenges that we are addressing, and this is our journey into that particular thing. And regarding solar DC as a technology, technology has won the IEEE Spectrum Award for Technology in 2017. And yeah, this is all about my presentation.
So that's a nice presentation, Mr. Shashi. Thank you very much for that. We have only now a few minutes to close the program. 12:30 was our last time, but we have few questions. We would like to take up a few of the questions. Some of the questions are already answered online. Now the question number one is, what are the BIS standards we have for 48 volt DC product? Is there any standard for wiring, distribution panel boards, etc. in 48 volt DC? So probably Rajiv Sharma ji can answer this.
Yeah, no, I'll answer. This is Rajesh.
Yes.
See, the standard is not an appliance standard. It's actually a distribution standard only. So the appliance standard will come later. Does that address the question?
Yes. Thank you. Thank you. So the appliance standards are on the way as they are.
That's right.
Gopaji, if I can just add here, as it was also told earlier in the presentation, that this is the starting point for the standardization. So first we needed to have a distribution standard in place, and then the component level standards, maybe the systems which will be the subsystems which will form a part of the standard. They are the work in progress, and the work is going on those subjects. Right. So this is the starting point, and this will pave the way for the other component level standards, which is work in progress at the moment. Not only here in India, but also at the IEC level.
Thank you very much, sir. That means we have more opportunities. Once when we make the standard, parallelly the products also can be.
Yeah, the entire ecosystem has to be built around the basic standard, which is already there.
Yes. Then the next question. Let me take up the next question. How AC overcurrent devices are used for DC system? Probably Mr. Rajesh can answer.
Yeah, it's no, it's a very tough question actually, because AC overcurrent devices they are meant for 230 volts. They can be used under some derating. So, for instance, there are some of these product literature which says that a 230 volt circuit breaker can be applied on a 24 volt DC system as well. But that's the kind of derating we are looking at. Whether it is whether you can use all 230 volt circuit breakers on 48 volt systems, the 48 volt DC systems, the answer is no. You have to really ask the manufacturer, whether it is applicable to be used in a DC system at 48 volts.
Okay, thank you very much. Now the question, next question, how it has coexistence with AC, since most of the appliances are AC driven in the industrial, commercial, and residential building.
No, the primary objective of the standard is how do we provide electricity access. It's more concerned with access, especially in a use case where there is no electricity available. So that is the first priority that the standard tries to address. But the question is, eventually, all these areas which are not grid connected will have some sort of a grid connectivity. So if it comes to that, how is this going? So let's say that there is a remote house which is being DC powered, and now there is a AC power, AC grid connectivity that is available. How would you use it? So the standard talks about the same approach. Use a isolating SMPS, right? So that's the only way in which this coexistence can happen. You need to use an isolating device, which will have 48 volts at the output and 230 volts at the input.
Yeah, thank you very much. Actually, now we have a long question. The question I will read, but it's already answered. While designing product in compliance with LVDC 48 volt, what guidelines are available for indoor and outdoor equipment? As Rajiv Sharma ji told, the standards for components and equipment are underway. These are not yet made. It is under making. So probably it takes some time to come out with some of the standards. Now there is a question: is isolation transformer?
Sorry, please, this is Vimal Mehru. May I just add a sentence to this answer that's given? You see, anytime you look at a standard for a certain use case, even if it is 48 volt standard for the use of electricity access, a standard cannot be seen in isolation. Typically, a standard is a combination of standards which get implemented. So, for example, in rural electrification access, the standard that is made, it has a cross-reference to multiple other standards. It could be wiring rules. The wires still have to be compatible. So the wire standards have to be referred to. The installation rules have to be standard to addressed. The plug-in socket standards. So there are some standards which are existing, which are referred to. IP standards, if you want to have a outdoor installation in 48 volts, which needs to protect from rain and ingress. So when you look at the standard for 48 volts, please read the list of other applicable standards so that you can have a look at the whole use case, not in isolation, just one standard. Thank you.
Thank you very much, sir. Thanks for the answer. Now the question is isolation transformer as an SMOT type or normal transformer is necessary? Also, do we need some DC link voltage as input for switching the TF.
Absolutely. So the see, I mean, the architecture of conversion is not a normal transformer. That is only for AC. So what is going to be used here is a switch mode, power supply, which is ideally a pulse transformer. So what you have is an input current. You will have some pulsing current at the input, which is defined by the switching frequency of the converter, and that would be through the electric flux, the energy will be transferred to the secondary. So it is going to be a switching mode transformer, or in general terms a pulse transformer, than a normal transformer which does AC, a voltage to voltage conversion. So because it's a switch mode transformer, or we are looking at a switch mode power supply design, DC link of course is going to be there, and that is 48 volts. So if you are looking at a system that involves a 48 volts distribution system, and you have a load that is let's say 12 volts, you will have a DC link which is 48 volts. Now, if you are going to derive this 48 volts from a 230 volt supply, then you will have a DC link which is 230 into √2, right? And that will have isolation there. In a 48 volts to 3 volts or a 5 volts conversion, you won't have isolation. That's the difference.
Okay, thank you very much, Rajesh. We have one last question. The question is, if we have voltage restrictions up to 48 volt, then what is to be done to meet overall wattage requirement for appliances?
Yeah, again, the appliance standards, are still, under the works. But the way if you look at DC appliances, right? So what we are looking at is a much lower power requirement for an equivalent AC device. So what's likely to happen when we, let's say that if we are going to have an AC mixer grinder, right? Now that would be rated about 1000 watts, but an equivalent DC mixer grinder would be some. I mean, I'm just shooting numbers off the cuff. Don't quote me. Is likely to be around 300 watts. So what will happen is that when there are going to be standards that right now we are looking at a tier 2 and tier 3 standards, where the appliance power consumption may not be too much, and even if it is, let's say, if you're looking at a power requirement of more than 250 watts, which is higher than what a single circuit can power, there are interesting scenarios wherein you can consider if there's a possibility of combining two circuits and actually enabling a 500 watt device to get to work on a 48 volts system. So these are some of the since we don't yet have a 48 volt appliance ecosystem. There is no mixer and grinder that is commercially available for 48 volts, even though people have designed. Unless the ecosystem is developed, it's difficult to answer specifically that question. But I'm just giving a generic answer considering the possibility.
Okay, thank you very much. Now I think we have answered almost all the questions. We have two people who has raised the hand. We already passed 4 minutes from our program. Can we answer these questions so that we can unmute them and take the question, Mr. Rajesh?
Yeah, sure.
We have the only email address I can see. This is vidyutclt@gmail. He has raised the hand. I have unmuted you, sir. If you have any questions, please we are there to answer. You can unmute yourself. And Dr. PC Kalra, your mic is also now enabled. You can, if you have questions, you can.
Good morning. I'm Lal, calling from Calicut, Kerala. I was about to ask about the wiring standards. Now that was also already answered in some of the questions. So
thank you.
Yeah,
Thank
wiring standard is part of this. You know, we recommend that the wiring is takes care of polarity considerations. There's also, I think, a wiring code as well, and also the thickness of the conductors. So these are the three things that are mentioned in the standards, with regard to wiring.
now my question is slightly different. Like when you consider AC, you have skin effect, whereas in DC you don't have that. So this multiple strand conductors will be replaced with single strand conductors. That is the basic question.
Yeah, so there is no great differentiation. The only thing is that single strand conductors may have some mechanical stability issues with respect to multi-strand. Single strand conductors are almost exclusively used in DC, not an issue at all, as long as you are able to ensure that there's no conductor fault because of that. That's all.
Okay, thank you very much, Mr. Rajesh and the gentleman from Calicut. There are a few more hands. Probably we will take up one or two questions more. We will take maybe 2-3 minutes more. There is a hand raise from Sumit Sen. You can unmute yourself, and if you have a serious question, please ask. If there is no question.
Excuse me, sir. May I put that feedback form?
Yes, please.
Thank you.
So for all the information in the chat box, we are putting the feedback form. If you can open up the feedback form and give us a feedback, and probably if you wanted to have the video link plus the presentation copies, please fill up the feedback form. We will send to you. Thank you very much. By this, I think probably we can close the session. Any comments from any other hosts or the presenters?
Thank you, Mr. Gopakumar. I'll make a quick comment. See, standardization is the only way the world can benefit from any technology. Today, we are very clear of the positives and benefits of direct current, but it requires all of us to get involved with the standardization activity. It is not the preserve of few to develop standards for the whole world. Unless as a nation, as a community, we get involved, we will keep lagging the rest of the world. It's a good thing that India is beginning to take the lead in DC standardization, but we can be the powerhouse. So I urge all members to actually, if there's one message I can give, it is, if you are engaged with it, you will lead the world in this standardization. Thank you.
Yes, that's what maybe probably it's a nice dream to have somebody calling from Germany in 2030 and asking us to bring some electrical appliance from India. Yeah, would be nice. So thank you very much. Thanks for all the support from BIS and all the participants and the attendees. So we would like to close the program. We are at least 10 minutes extra. Thank you very much. Thanks to all.
Thank you so much. Thank you. Bye-bye.
Thank you, Mr. Gopakumar.
So we end up the program.